Okay, so the next thing I want to talk about is continuity. And continuity, there it is. So and continuity is kind of like your next step in terms of we're looking at limits and seeing if limits exist. And then sort of like the next thing we're going to analyze is how the function's behaving. Is it continuous or not continuous? And you probably have an intuitive understanding of continuity or something that's continuous or connected, and your intuitive thought is that, if you draw a line and you don't break it up or anything like that, that this is a continuous line. So your intuitive thought is right. But if for some reason you are drawing a line and you pick up your pencil and you come over here and maybe you come over here, that is not continuous. And so, we want to formalize that in terms of calculus. So there's three things that have to happen for you to show or prove that a function is continuous at a point. And notice that C, that is one, like I said, that's one specific point. So we could say at a point. And I think I'm going to go even thinner on that, just because that was a little bit thick. Okay, so continuous at a point. Okay, so three things have to happen, and it's building off our idea of limits. So it's going to have limits in its definition. So the first is the limit as x approaches C, this point in question, from the right of f of x is defined, is, let's say, equal to, or is defined, and maybe you could say it's equal to, that color, equal to some constant value, call it k. Okay, so some unknown value. Okay, so the limit as x approaches this unknown point from the right is defined at some k value. Okay, and notice that again we're coming from the right. That's half the battle. Now you can anticipate that we have to come from also the left. And there it is. So the limit as x approaches that same value of c from the left of f of x is also defined, and it's the same value. It's defined and is the same k value. Okay, so we want, and again, if you think about this potentially from a graphical point of view, so here's your c value, remember, because it's an x value. And you're coming from the left, so here's your function, and let's say it equals that point right there. That's a k. And you're coming from the right? So they're lining up towards each other. But the thing is that your limit from the left and right could be equal to each other, but your function would not be continuous unless that hole is filled in. So how do we determine that? We need to make sure the actual function value f of c is equal to that k value. And so the function has to be defined there. So the limit from the left has to equal the limit from the right, has to equal the function value. Now notice there are no limits here, right? It's just the function value. And then another way to think about this, is we're saying the limit value, because that's what that's what part 1 and part 2 are talking about. The limit value is equal to the function value. And, again, another way to think about this is that, well, what should have happened did happen, right? There were no surprises. Because when we are evaluating limits, remember, we sort of put a vertical bar here, right? We try to ignore, well, what's really happening? And we don't care if there's a hole there or a jump there for a limit to exist. But now I want to go one step farther and say, okay, well, wait a minute. Now I want to make sure the behavior behind that bar actually is doing the right thing. Okay, so those are three things: the limit from the left, limit from the right, and then the function value itself is defined. Now, in this course, we will be proving continuity at a point. But if you could somehow prove that you're continuous at every single point on an interval, then you could say that you were continuous on on that whole interval. So I'm not, that's kind of, I think, why I have that there on my notes. Oops. For some reason. Go thinner. There we go. Okay. A function is continuous on the open interval if it is continuous at every point. If it is continuous at every point C on that interval or in that interval. And that's hard to prove at every single C value because there's an infinite number of C values on that open interval. So again, we would just be looking at the whole interval, like the interval as a whole, and trying to identify one point, maybe it's continuous or discontinuous. Okay, now there are two different types of discontinuity. The first type of discontinuity is called non-removable. And it's you don't have to memorize that it's, this is type 1, non-removable. Okay, so a non-removable discontinuity. So an example of non-removable, go back to here. So one example of a non-removable discontinuity is a jump. So you could be defined everywhere. Here's your function, but there's a jump. Maybe it was part of like a piecewise function, right? There's a jump. And so here, the limit from the left does not equal the limit from the right. So that's discontinuous at that jump right there. Okay. Another kind of discontinuity is a vertical asymptote, which you could argue is a jump in a way, right? You have to jump across the asymptote to get to that function. But so if you have a vertical asymptote, let's say right there, and you have your function, maybe it goes up, and then maybe it comes from here, right? So if you have a vertical asymptote, it's all over the place there. Vertical asymptote. Okay, that's another type of discontinuity. Okay, now the third type is it's kind of a weird thing. It's an oscillation. And sometimes I kind of joke, I call this like death by oscillation, because here's what happens. As an example, if you think about the function sine of 1 over x, okay? So sine of 1 over x. So if you think about as x gets close to 0, 1 over 0 is undefined. But as x gets close to 0, before you get to 0, right, before you get to the undefined point, this fraction as a whole becomes larger and larger and larger. But then the sign of that value, no matter how large this value is inside, the biggest output sign can give you is 1. And the smallest output sign can give you is -1. So what ends up happening, and this is kind of a crazy graph, so what ends up happening is that when you're away from 0, you look like your sine function, right? Just nice and nice and nice, right? Same thing over here. Your sine function's very nice, aesthetically pleasing. But all of a sudden, you start getting closer and closer to 0. And what happens is that your frequency increases, right? Your wavelength decreases, your frequency increases. So all of a sudden, your sine waves are compressed tightly together. And you're just basically oscillating, as you get closer and closer to 0. Now, that's not a hole. It's not an asymptote. It's not a jump. It's an oscillation, and so it's definitely undefined at 0. So like you go back here like this. So it's not defined at 0, but the limits from the left doesn't exist, limit from the right doesn't exist, because as you get closer and closer and closer to zero, you become oscillating so quickly. So those are the three kinds of non-removable features of discontinuities: jump, vertical asymptote, and an oscillation. Okay, you cannot remove those. Now, you do have one kind that we haven't talked about, which is removable, and that's the one that we actually looked at, interestingly enough, in yesterday's lesson. Okay, so if it's removable, that means you are a hole. Okay, there's only one kind of removable discontinuity, and that is a hole. And so if I take a look here, and I draw a function, there's a hole. So even if it's defined like up here, right? So I know it's not continuous because the limit value is down here, but the function value is up there. But this hole is removable, and we can call it removable. And the reason it's called removable is because of all the discontinuities. Oops. It's the one that you can fix. That's what I'm looking for. This there. So this hole could be just put right there. Like I could somehow redefine the function, and so that of all the discontinuities, that's the discontinuity that's easiest to analyze, because that's the discontinuity that we can actually reassign. Okay, so again, two different types of discontinuities: non-removable versus removable. And then, like I said, there are three examples of non-removable, one example of a removable. We will be using this definition of what it means to be continuous to prove things. So you want to remember, you have to show from the left, show from the right, and show that the function values all are equaling the same thing. And we'll see like what happens if one doesn't. Then you can prove that it's discontinuous, and you just have to show that one of them doesn't equal the other two. Okay, so excellent. So very nice. And then let me know if you have any questions on the video.